This is lesson 16.1, the scientific revolution. Why did revolutionary scientific discoveries occur in Europe during the 16th and 17th centuries? College Board Topic 4.1, contextualizing the scientific revolution and the Enlightenment. The rediscovery of works from ancient Greece and Rome and observation of the natural world changed many Europeans' view of their world. Explain the context in which the scientific revolution and the Enlightenment developed in Europe. New ideas in science based on observation, experimentation, and mathematics challenged classical views of the cosmos, nature, and the human body, although existing traditions of knowledge and the universe continued, even among scientists. And then we've got topic 4.2. And we've already seen this, the rediscovery of works from ancient Greece and Rome and observation of the natural world changed many Europeans' view of their world. Lots of repetition in the College Board topics. And it says, explain how understanding of the natural world developed and changed during the scientific revolution and the Enlightenment. New ideas and methods in astronomy led individuals, including Copernicus, Galileo, and Newton, to question the authority of the ancients and traditional knowledge, and to develop a heliocentric view of the cosmos. But then, look at this one. Alchemy and astrology continued to appeal to elites and some natural philosophers. That's a scientist, by the way. In part because they shared with the new science the notion of a predictable and knowable universe. At the same time, many people continued to believe that the cosmos was governed by spiritual forces. Places still very much the same, especially East Prussia, Bohemia, Denmark, Florence, and England. Key players of the scientific revolution: Nicolaus Copernicus, Johannes Kepler, Galileo Galilei, Tycho Brahe, and Sir Isaac Newton. And we've got key concepts of the scientific revolution: the crystal spheres, the law of inertia, law of universal gravitation, heliocentrism, and natural philosophy. Well, where do we even begin? What three developments inspired the scientific revolution? We can sum it up to, number one, the university, number two, the Renaissance, and number three, technical advancements. But first, why didn't it happen in other places? Let's explore some other places where the scientific revolution perhaps could have happened, but didn't. Why didn't it happen in the Islamic world? Muslims had ancient Greek learning. Muslims had interaction with vast peoples and cultures. Muslims had relative tolerance of religion. Of course, nobody's tolerance was great during this time. Nobody gets any prizes for religious tolerance during this period. They had a scholarly language, Arabic. They had many important cultural centers. They had the first universities. They had surpassed the ancients in many areas: math, like algebra, algorithms, decimals, physics, astronomy, navigation, navigational instruments, medicine. The Islamic world also never experienced any kind of regression like Europe did. They had never experienced a total collapse of their institutions. But there were reasons that it didn't happen in the Muslim world. Number one, after the Mongols collapsed, there were three surviving empires: the Ottoman Turks, who we've studied, the Safavids in Persia, and the Mughals in India. And top priority for them was, number one, to restore order, and number two, to assert their legitimacy. And how would they do that? They wanted to get back to tradition. They wanted to impose universal Islamic orthodoxy. They wanted to clamp down on innovation, and they wanted to reject the printing press. And so they failed to adopt the printing press, the key component in the dissemination of knowledge. Of course, hindsight's 20/20. China, why didn't it happen there? I mean, they had lots of scientific activity going on. They had influenced Europe for centuries. They had paper making. They had gunpowder. They had silk. They had the compass. But there were reasons that it didn't happen in China either. Number one, politics got in the way. There was a new dynasty, the Qing dynasty, and they also wanted to assert their legitimacy, and they, like the Muslims, did it by universal adherence to tradition. What about Mesoamerica, way over on the Western Hemisphere? What about the Maya and the Aztecs? They had complex calendars. They had advanced astronomy. They had highly developed mathematics. They had developed writing. But there were also reasons that it didn't happen in Mesoamerica. Something made the Maya simply, well, not exactly go away, but regress quite a bit. The reasons were probably economic in nature, and the Maya civilization collapsed around 900 AD. They were still around, and they even had large cities, but they certainly weren't dominant when the European explorers conquered Mexico. The Aztecs were conquered, as you know, by Hernán Cortés. Reasons that happened in Europe. Europe had strong monarchies by this time. We've been studying that. We've been talking about that. And these monarchies led to a growth in trade. Trade led to a renewal of learning. Universities were founded, teaching Aristotle. And Europe had Renaissance humanists who wanted to restore the glory of the ancient classic texts. There was a quest to supplement the current knowledge of classics, which they felt was lacking, with rediscoveries, more manuscripts, and this was especially true after the fall of Constantinople in 1453. Byzantine Christians and scholars fled the Ottomans with lots of ancient texts. So new knowledge in math, astronomy, natural philosophy was entering the universities in the forms of these new types of professorships. And these professorships taught not just for practical applications like accounting and surveying, etc., but for understanding the world. Let's look at Hans Holbein the Younger's famous 1533 painting, The Ambassadors, which he painted in England. This painting brings together several of the things that we've been learning: the Renaissance, the Reformation, exploration, scientific revolution. Ambassadors were a product, as we know, of civic humanism. And the technical detail and the symbolism of the Northern Renaissance is found in this painting. One of these two guys is secular. One of these two guys is clergy. And you've got these two shelves. The top shelf is filled with all kinds of navigational and scientific instruments, and globes, and an exotic rug, because you got to do some traveling to find exotic rugs. But the lower shelf, it's got a Lutheran psalm book, and it's got a lute with a broken string. Religious discord. There's a weird, prominent, distorted skull, a Renaissance symbolic technique. That weird skull right there, that wasn't superimposed on the painting. That's actually part of the painting. Overseas expansion. Dangerous conditions called for better instruments, barometers, thermometers, telescopes, etc. Better instruments gave you better observations, and better observations gave you better knowledge. Europe had the printing press. Knowledge disseminates better, gets to more minds. More minds can join the discussion faster. Europe was politically fragmented. It's got lots of competing kingdoms and principalities, and you might say that's a bad thing, but there's also no one dominant orthodoxy that everybody has to adhere to. Before 1500, the term science actually didn't exist. The term people used was natural philosophy. There were two pillars of science before 1500. You had Aristotle and you had Ptolemy. So let's look at Aristotle first. He provided the basic foundation of knowledge about physics. But he was wrong about a lot of things. He taught that there were 4 imperfect elements on the earth: earth, fire, wind, and water. He also taught that the heavens were made up of this 5th element that was called quintessence. And that element was perfect. Quin actually means 5th, so it's the 5th essence, quintessence. He taught that all of the heavenly bodies were embedded in an interlocking series of crystal spheres above the earth, like one of those Russian babushka dolls. You know how there's one inside the other? Ptolemy. He provided the basic foundation of knowledge about the earth. He invented latitude. He used 360 degrees. He explained planetary motion with these things called epicycles and deferents. And I kid you not, I've actually seen a test question on that subject. Well, both Aristotle and Ptolemy pushed our understanding forward, but both Aristotle and Ptolemy had severe limitations and inaccuracies. Spirograph. Here's my explanation of Ptolemy and what we're talking about when we're talking about epicycles and deferents. When I was a kid, you had this popular toy set called Spirograph, and it came with all kinds of toothed wheels that you could stick a pencil through and make tons of beautiful designs. And we didn't know at the time, but we were actually working with epicycles and deferents. So Ptolemy's theory of planetary motion went like this. Planets, they're up there in this perfect quintessence, but they seem to wobble as they orbit the Earth. Now, why would they do that? Ptolemy explained why with this idea of epicycles and deferents. Each planet revolves around its own epicycle, and the center of each planet's epicycle goes around its own deferent. So each planet's deferent goes at a uniform speed around a center, and the Earth is slightly off center. And so basically that's how he explained planetary motion. But he didn't completely debunk Aristotle's idea of the crystal spheres. If you're going to challenge these ideas of Aristotle and Ptolemy, here's what you need. Number one, you need precise techniques, observation, experimentation. Number two, you need to separate your findings from philosophy and from religion. And number three, you need to do the math. When and where you can, you've got to put your arguments in mathematical terms, numbers, calculations, formulas. And why? Because numbers don't lie. Numbers are objective. They're universal. They're pure. Everybody speaks the same language when it comes to numbers. So Aristotle's crystal spheres, the thing you got to understand about the crystal spheres is it's a theory that really makes sense. So what can we say about crystal? Everybody's got crystal at home, right? You think of a crystal bowl that you've got at home, right? How can you describe it? It's perfect. It's solid and unchanging, never changes. It's transparent. You can see through it. You can embed things in it, like decorative stuff in it. It's invisible. Solid layers of crystal around the earth makes sense. And it explains why some objects move congruently up there in the sky and some don't. For example, the stars. They appear to move, and they appear to move all together. So it seems as if they must exist within some kind of unifying structure, right? Now, keep in mind, in Aristotle's universe, there's no such thing as space. And so the heavenly bodies are all very, very close to the earth. So when you account for all the different movement patterns of all the heavenly bodies that you can see, you come up with about 10 or so crystal spheres. And then beyond them, right, beyond that top one, that outermost one, you have heaven. And that was the structure of the universe as Aristotle understood it. It's actually quite a small universe. Well, who are these early scientists? We'll come back to these crystal spheres. These early scientists, they're of noble birth, noble enough to get an education. They're not really rich at all. They are all deeply religious. They were all prepared for religious careers. Their scientific discoveries do not undermine their religious convictions at all. And they come from traditions which honor things like alchemy, astrology, even magic. Nicolaus Copernicus, 1473 to 1534, Polish church cleric, actually. This idea of heliocentrism, right, the idea that the solar system goes around the sun, that was not his own invention. He got that idea from Greek and Arab scholars. Copernicus, like all of these scientists, was deeply religious. He worked for the church. And he worked on heliocentrism, this idea, for over 30 years. And he wrote his findings down in a book called On the Revelation of the Heavenly Spheres. Copernicus waited 13 years to publish this book. He actually published it on his deathbed. So he waited until he was about to die to publish it. And it wasn't because he was afraid of the church's reaction. He wasn't. He was actually afraid that other scholars would laugh at him, make fun of him. The implications of Copernicus's book. Stars are at rest. It's the earth that is moving. Aristotle's crystal spheres are now being called into question. The implications of Copernicus's book. And this is kind of hard to explain, but I'll try to. The stars are at rest and the earth is moving. Aristotle's crystal spheres are now being called into question. If Copernicus is right, then the universe must be unbelievably vast. Keep in mind, Aristotle's universe is very, very small. And the reason that the universe must be unbelievably vast is this. You see, if the Earth goes around the sun in this huge orbit, then there should be, from our point of view, standing on Earth, there should be an observable, what they call stellar parallax. That's what astronomers reasoned, right? In other words, there should be a corresponding shift in every star's position relative to the Earth's between January and July. In other words, they should look like they're making little circles, right? But the problem is, the stars don't seem to be doing that. In that case, if the stellar parallax is so tiny that it can't even be measured, can't even be observed, then that could only mean one thing. Those stars are way, way, way out there. See, with Copernicus, the universe just got unbelievably bigger. Math suddenly became much more important. Up to this point, math had been considered a lesser discipline, but now you had to be able to crunch the numbers to figure out what was going on. If the Earth is just one of the planets, where does the earthly sphere end and the heavenly sphere begin? Man had always believed that God and heaven were just beyond the highest, the outermost of those crystal spheres. But if there are no crystal spheres and the universe is huge, then where's heaven? The reaction to Copernicus depended on how literally you wanted to take the Bible. The Catholic Church actually waited 73 years to declare Copernicus false. In the 1570s, two important phenomena occurred which brought Aristotle's crystal spheres model of the universe into even more doubt. First one, in 1572, a new big star showed up in the sky, and it shone brightly for 2 years and then disappeared. Now today, we know now that that was a supernova. And then in 1577, a new comet appeared in the solar system, and that comet appeared to cut a path straight through the crystal spheres, if they're up there. The crystal spheres, if they're truly up there, didn't even seem to slow this thing down. These two things, right, this new star and this new comet, these things weren't supposed to happen if the crystal spheres up there were perfect and unchanging. Tycho Brahe, 1546 to 1601, Danish guy. At the beginning of his career, Tycho Brahe made close observations of that new star I just talked about. And his observations impressed everybody. The Holy Roman Emperor Rudolf II set him up with his very own observatory. Brahe worked for the church, and he collected massive amounts of data over the course of 20 years. And he developed the Rudolphine tables of planetary motion. The problem with these tables, however, was that the observations didn't add up mathematically. Then he died, leaving his assistant, Johannes Kepler, to try to somehow make sense of all these observations that didn't add up mathematically. And so Johannes Kepler, 1571 to 1630, Kepler actually managed to get Brahe's observations to make sense. He formulated the 3 laws of planetary motion. Now, that sounds really complicated, but if you have ever used a yo-yo, then you can easily understand the 3 laws of planetary motion. Here they go. Number 1, planets' orbits are not circular. They are elliptical. Number 2, planets don't move at the same speed all the time. Think of a yo-yo. You know the yo-yo when it's way out there, like you got the string strung out way far. You know that yo-yo is not moving as fast as it does when it comes in really close, right? When they're far away from the sun, they slow down. When they come back close to the sun, go around the sun, they speed up. Number 3, how long it takes a planet to complete an orbit is precisely related to its distance from the sun. Think of the yo-yo, right? Or even better, think of tetherball. What happens when that ball goes around the pole and the tether gets shorter and shorter and shorter? What does that ball do? We've all seen it. We call these things laws because Kepler didn't just claim these things. He convincingly demonstrated them with math. Kepler also came very close to formulating the law of universal gravitation. Newton did that in large measure by studying Kepler. Where was the Catholic Church this whole time? Scientific minds of the Catholic Church, and there were some really good ones, were actually not worried about the heliocentrists like Nicolaus Copernicus, Tycho Brahe, or Johannes Kepler. And here's the reason. Even though Johannes Kepler formulated the laws of planetary motion, he could not explain the mechanics of that motion. In other words, Kepler couldn't tell you why it was that planets move at all in the first place. If anybody could explain that, then the Catholic Church would start worrying. Galileo Galilei, 1564 to 1642. He was a science guy. He loved science, loved everything about science, loved the observation, the experimentation, the demonstration. He formulated the law of inertia. We call something a law when it produces the exact same result, the exact same way, every time, without exception. And the law of inertia says this: an object is at rest only under specific conditions. And if those conditions are not present, then those objects are much more likely to be moving perpetually. Let me see if I can explain that. Put something on your desk, like let's say your phone. Now, your phone is sitting on your desk. It's not moving. And it looks to you like that's its natural state. However, the reason your phone is not moving on your desk is because of a specific set of conditions. For example, the weight of the phone, the friction caused by the desk, the friction caused by the surface of your phone, gravity. All of those things are working to keep your phone stationary. If those conditions did not exist, your phone would actually be moving around the room. Galileo conducted motion experiments using balls on a flat, hard surface, because if you've got a surface like that, you've got minimal friction acting on that object. Galileo was also an accomplished instrument maker. He built his own telescope based upon a written description of one. He found 4 of Jupiter's moons, and that's another problem for Aristotle's crystal spheres. Here's the problem. Galileo said that Jupiter can't possibly be embedded in a crystal sphere if it has moons moving around it. Galileo also observed the moon, and he found that its surface was not perfect at all. It was all pockmarked and mountainous in random places. Now, how can that be if the moon is supposed to be made of quintessence, which is perfect? Galileo wrote a book called The Sidereal Messenger in 1610. Sidereal means starry, and often this book is called The Starry Messenger. It's all the same book. And in this book, he described his telescope observations, and he contemplated their meanings. And in 1616, the Roman Inquisition ordered Galileo, quote, not to hold or defend the Copernican position. Well, in 1623, Galileo wrote a book called The Assayer. And this book advocated experimentation and mathematical formulation of scientific ideas. This book was highly successful, and it even got support from church leaders. So it looked as if, at this point, Galileo and the church, they were going to be okay with each other. That's not going to last long. But we'll come back to that later. Let's go on to Isaac Newton. Isaac Newton, 1642 to 1727. Isaac Newton was extremely focused on math. He took all the scientists that we have discussed so far, and he did something extraordinary with them. He synthesized all of their teachings into mathematical proofs. And in 1687, Galileo wrote The Mathematical Principles of Natural Philosophy. And in it, he formulated the law of universal gravitation. And what he said in the law of universal gravitation was this: gravity works the same way everywhere, every time, without fail, whether we're talking about on Earth or in the heavens. And you can calculate the amount of gravitational force an object exerts on another object perfectly. It goes up with mass and down for distance. So, New World exploration and the scientific revolution. Advances in astronomy were also changing people's worldviews in botany, zoology, cartography, metallurgy. How did we acquire all this knowledge? Well, to a great extent, we learned it from people who already knew it. For example, Philip II's physician, Francisco Hernandez, he spent 7 years in the New World collecting knowledge from the Aboriginal people, the native people, and volumes of information were created just from that endeavor alone. Carl Linnaeus, 1707 to 1778, he was a Swedish biologist, and he was kind of like the Henry the Navigator of biology. He sent his students all over the world. They collected samples and observations. Linnaeus started a system of classifying species of plants and animals. Unfortunately, he also kind of started doing it with human beings, and he had some racist biases that he put in that also. Old traditions die hard. We just saw that with Linnaeus. Most scientists came from older traditions that were still well respected. For example, alchemy. Alchemy was a medieval chemical science and speculative philosophy that was aiming to achieve the transmutation of the base metals into gold. The discovery of a universal cure for disease, that was another aim of alchemy. And the discovery of a means of indefinitely prolonging life. All of these were goals of alchemy. Newton himself was fascinated by alchemy. Many believed that his 1687 book was really just alchemy. Astrology. Johannes Kepler used astrology to guide all the major decisions of his life. Johannes Kepler wrote at length about balance and harmony that he observed in planetary motion. He often used music and the various harmonies in it as an analogy for planetary motion. And get this, Johannes Kepler also believed in magic. In fact, Kepler's own mother, Katharina, was tried for witchcraft.